All right, today we're diving into this really cool, kind of strange idea in AI. What happens when you teach one machine to be like a master art forger and another to be an expert detective, and then you make them go head to head?
So let's get right into it. The core question here is actually pretty profound. How can a computer learn to do more than just recognize things? How can it learn to create something totally new and believable? Something that looks, for all intents and purposes, completely real.
Well, the answer is this really clever setup with two neural networks that are basically rivals. So on one side, you've got the generator. Think of it as our master forger. Its whole job is to create fakes that are just perfect. Then on the other side, you have the discriminator. This is our super sharp detective, and its only goal is to spot the difference between a real masterpiece and whatever the forger just cooked up. And this whole system? It's called a Generative Adversarial Network, or GAN for short. The core idea is just brilliantly simple. Competition makes you better. By constantly trying to outsmart the detective, the forger has no choice but to get better and better at its job, until it's making fakes that you just can't tell apart from the real thing. Okay, so how does this rivalry actually play out? I mean, this isn't just some abstract idea, right? It's a real dynamic training process. How does one network's mistake become the other one's lesson? How do they both level up from this? It's all set up as what's called a mini-max game. That's really just a fancy way of saying it's a zero-sum game. Think about it. Every single time the detective correctly spots a fake, it scores a point, and the forger loses. But every time the forger manages to slip a fake past the detective, the tables are turned. One's win is always the other's loss. No middle ground. And this all happens in a continuous loop. So step 1, the generator churns out a bunch of fakes. Step 2, the discriminator looks at a mix of those fakes and some real data, and it tries to sort them out. Step 3, the discriminator gets a little update based on how well it did. And then step 4, and this is the really critical part, the generator gets an update based on how successful it was at tricking the discriminator. This whole cycle just repeats over and over, turning this game of cat and mouse into an incredibly powerful learning engine. But just like any competition, this whole thing can fall apart. The system is actually pretty delicate. So what happens if one side gets way too good, or maybe even gets a little lazy? The entire learning process can get thrown completely out of whack. A classic example of this is something called mode collapse. This is basically where our forger gets lazy. It figures out one specific type of fake that works really well at fooling the detective, and then it just makes that one thing over and over and over again. I mean, it might be a super realistic fake, but it totally misses the point. It fails to capture all the variety of the real world. Like, imagine you're training again on faces, and all it ever learns to create is one single realistic face. That's mode collapse. And mode collapse is just one of the big challenges. There's another really tricky one called vanishing gradients. Okay, so think of a gradient as the feedback, the clue that tells the forger how to get better. Now, what if the detective becomes so good that it's basically perfect? It just says fakes to everything with no real feedback. Well, then there are no clues left. The signal just vanishes. And if the forger has no idea how to improve, its learning just grinds to a complete halt. So yeah, the big question becomes, how do we fix this? How do we rebalance the whole game and keep it fair? And more importantly, how do we keep it productive so both networks can actually keep learning and getting better?
One of the biggest breakthroughs was changing the scoring system, what's technically called the loss function, basically how we keep score of who's winning. The original way was like a simple pass or fail test, and that's what led to that whole vanishing gradient problem. The solution came with something called the Wasserstein GAN. It uses a totally different idea called Earth mover's distance. Just imagine you have two piles of dirt. One represents all the fake data, the other represents the real data. This new method doesn't just say, yep, they're different. Instead, it calculates the actual work it would take to reshape the fake pile to look exactly like the real one. This gives the forger a much more useful, continuous score of how close it's getting, which means it can learn even when it's way off. And it wasn't just about new scoring rules. Researchers came up with a bunch of other smart techniques to keep the game stable. For instance, there's mini-batch discrimination. This lets the detective look at a whole group of fakes all at once, instead of just one at a time. This makes it way easier to catch the forger if it starts getting lazy and just churns out the same image again and again. It's little tweaks like this that really help turn GANs from a cool but finicky idea into a seriously powerful tool. So, okay, now that we have a game that actually works reliably, we can start asking it to do more. We can move beyond just creating random, realistic-looking stuff and start steering this incredible creative engine toward specific, really useful goals. And we do that with something called a conditional GAN, or CGAN. The idea here is pretty simple. You give both the forger and the detective an extra piece of info, a condition. So instead of just saying, hey, make a realistic image, we can now say, make a realistic image of a cat. Now the generator has to do two things: make an image that's believable and make sure it actually matches the request. This one simple tweak, it just blows the doors wide open for all sorts of amazing applications, like image-to-image translation. I mean, think about it. You could turn a satellite photo into a street map, or a black and white picture into a full color one. You could even take a simple little sketch and turn it into a photorealistic image. It's wild. A really famous model that does this is called Pix-to-Pix. It's amazing for things like taking architectural plans and generating a realistic building facade from them, but it has one big catch. It needs a training dataset of perfectly matched pairs. That means you need the exact sketch and the exact photo that goes with it, the exact map and its matching satellite image. That can be tough to get. Right, so what if you don't have that perfectly paired data? Let's say you want to turn a photo of a horse into a zebra. You're never going to find photos of the exact same horse in the same pose, but one's a horse and one's a zebra, right? It just doesn't exist. Well, this is where CycleGAN comes in, and it is just brilliant. It solves the problem by learning to do the translation in both directions at the same time. So it learns to turn horses into zebras, and it learns to turn zebras back into horses. Then it uses this check called cycle consistency to make sure that if you take a horse, turn it into a zebra, and then turn it back, you still get your original horse back. It's just such an elegant solution to a really tricky problem. So in the end, what starts out as this intense competition between a forger and a detective, it actually turns into this weird creative partnership. It's a process that shows that through pure adversarial pressure, a machine can learn to take completely random, meaningless noise and shape it into something that looks, feels, and is as convincing as reality itself. And that kind of leaves us with one last, pretty deep thought. As these generative models get more and more powerful, creating fakes that are perfect right down to the last pixel, what does that mean for how we define what's even real anymore? If you enjoyed this explainer and found it useful, please do us a favor and like, share, and subscribe for more.